Welcome, Thermo students. Today is Thursday, September 10th, and we'll have a good time today, I'm sure. Let me see who we got here. We have, a good crowd. Alex, Anna, Daniel, Dawson, Julian, Bryce, Tyler, Reagan, Nicholas. Did I leave anybody out? I guess that's pretty much it. Let me see what we're going to do today. Okay, well, we got a good crowd, and we're in Thermo now. And did you know there's an exam, and I think it's posted already. Yeah. It's due the 13th, which I think is Sunday night. Today's Thursday. Friday would be the 11th. Saturday, yeah. Sunday night at midnight. It's a take-home exam, open book, open note. You should do just fine on that exam. It should be on Blackboard now. And as far as homework goes, I'm a little behind grading my homework, but I'm going to catch up. I'm going to catch up and post all of your homework grades. But I'm not going to give you any homework tonight. You lucky people. No homework. And then when we start on Monday, Tuesday, when we start on Tuesday, we'll be in chapter 3. I guess you could say the homework is to read chapter 3. So here, we'll make a note of that. Your homework is to read chapter 3. Work on your exam, get it in by Sunday night. That'll work. But before we begin, what we're going to talk about today, if you want to know the topic, is one of the most important things in this class, and that's your PV diagrams. You've got to master those PV diagrams. But before we begin, did anyone have a question for me?
Yes, Mr. Griffin, I have a question.
Yeah.
I have a question on the exam.
Okay.
I was looking at question 1. Do you expecting us to draw the PV diagram? Because you didn't mention any PV diagram on the question 1 and question 2 until the last question. And you say we can scratch the PV diagram on the last question. I'm a little bit confused.
Okay. Well, let me think just a minute. It's Reagan. I'm talking to Reagan, aren't I?
Yes.
Okay, just a minute, Reagan. While I think, I'm thinking and I'm thinking. Okay. I'm not sure I know the answer to your question, Reagan. Right now, I could figure it out, but here's the rule. If in doubt, draw a PV diagram. But unless they specifically ask for it, it will help you. It'll always help you, and it's a good idea to draw a PV diagram, but it won't count off on your grade if I don't ask for it. If I ask for it, and you don't do it, that will count off on your grade. Did that answer your question, Reagan?
Yes, I think you did.
Yeah, it's a good idea always to draw it, but it's unless I ask for it, it's not specifically required. But we have to understand them. Anybody else?
Yeah, on the exam, should it be turned in on the engineering paper or on the print off from Blackboard?
Either one. I would really prefer the print off on Blackboard. Now, who am I talking to?
Tyler.
Tyler. Yeah, I would prefer the print off on Blackboard, Tyler.
Okay.
But I would accept it on engineering paper. Anybody else? Anybody else? Okay, well, let's practice. Here's our topic. I don't think it'll hurt us to practice that. Let's suppose that you had, I'll give you a problem to work here. Suppose you had air at 150 kilopascals. You got air at 150 kilopascals and specific volume of 0.38266 cubic meters per kilogram. Okay, we're going to have a isothermal process. And what that means is constant temperature. We're going to have a constant temperature process to 100 kilopascals. So what I want you to do is first sketch the process on a PV diagram. Sketch the process on a PV diagram. And two, find V2. Now you see we know V1 and we know P1. That's P1 right there. We're talking about air now. And it's an isothermal process. So let me help you a little bit. The first thing we got to do is find out what the temperature is on this isothermal process. Since it's air, you get to use the ideal gas law at these temperatures. So P1 V1 is equal to RT1. Now we know P1. It's 150 kilopascals. We know V1. It's 0.38266. You can look up R. And you can find T1. I'm going to shut up for 1 minute, and I want you to find the temperature. Go for it. I want everybody to find the temperature. Go for it. And you're going to have to look up that R. Let me ask one of my students what that R is. Let's see. How about my friend Bryce? Bryce, unmute and tell the gang what R is.
Yeah, I found 0.287.
Good going. Thank you, Bryce. Well, as long as I've got Bryce on the line there. Bryce, did you find out the T1 yet?
I've got rounded to 200.
Good going, Bryce. Well, if T1 is 200, now will that be Kelvin or Celsius, Bryce?
That's going to be Kelvin.
Yeah, it's gonna be Kelvin. Good going. You can put units in brackets if you want to. So if that's T1, what's T2? If it's an isothermal process, what would T2 be, Bryce?
It's going to remain 200 Kelvin.
Good going. It's an isotherm. Temperature is going to stay the same. Now what I want you to do, all of you, I'll pick on somebody else besides Bryce now. I want you to sketch that isotherm on your PV diagram. I will shut up for a tiny minute and we'll ask one of my other excellent students how they did. Go for it. Sketch it. Well, okay, I'm gonna sketch it now. I need a little room here. I can say goodbye to all that stuff. That'll be fine. And we'll sketch the isotherm. Now we're starting off at 150 kilopascals. There we go. And a specific volume of 0.38266. Okay, great. And then I like my isotherms in red. So let's get a red color here. And what we're going to do is we're going to come down here like this. See, isotherms do this. There's a name for that shape. It's called a hyperbola. And we're going to come down here to V2. We're going to find V2 here in a minute. And see, here's state 1. Here's state 2. And here's our process. This is an isotherm. Now, did you notice we didn't put any vapor dome? You know how I usually draw one of these things? We didn't put any vapor dome on there because, see, a vapor dome is where you have a saturated mixture. You have part liquid and part vapor. Well, we don't have any liquid. We're talking about air here, and at these temperatures, at a temperature of 200 degrees Kelvin, 200 Kelvin. Well, actually, that's still that's pretty dang cold, really. It's minus 73 Celsius. You're up in Siberia in the wintertime, okay? But air has still not liquefied. So you still have a hyperbola there. Maybe I should go over hyperbolas with you. But first, let's go ahead and get your specific volume at state 2. Now to do that, we're going to treat air as an ideal gas in this class, because we're always going to have temperatures where it doesn't liquefy. So we're going to have P2 V2 equals RT2. And we know T2. And one of my students helped us with the R. R is 0.287. Isn't that what it is? Did I do that right? 0.287? Somebody
Yeah.
say, uh-huh. Yeah, that's right. And we know what P2 is. It's 100. So you can solve for V2. And go ahead. I'm going to solve for it. You solve for it. Get your V2. Go for it. See, we're gonna come down here to 100 kilopascals, and the V2 is well, I got an answer. I'm not sure this is right. Did anybody get 0.574?
Yeah.
Yeah,
Yes.
that's two of us. Anybody else?
Yeah.
Yeah, okay, I bet I did that right. Now when you do these, I like it if you label everything. Notice I labeled that's my P2 right there. This was P1. Hey, look, here's your V1 and your V2. See, the V2 is the 0.574 cubic meters per kilogram. And see this isotherm? That's a 200 Kelvin isotherm. Look, I labeled it. And on my process, I put a 1, I put a 2, and I'm going to draw my process now. There it is. And there's an arrowhead. See that arrowhead? That's what I want to see. I want to see a 1 and a 2, and I want you to draw the process with an arrowhead on it. I'm getting homework from you guys, and you're making a PV diagram, and some of you even have a 1 and a 2, but you won't draw the process for me. Draw the process. And if it curves, follow the curve. Do not go shortcuts where you go from 1 straight to 2, because it doesn't do that. This is an isotherm, and it follows that red line, like follow the yellow brick road. There you go. From Wizard of Oz. Yeah, you follow the yellow brick road. You don't go off into the forest. No shortcuts, please. That's what I wanted. And we found our V2. Any question on this? We're just going to run through a bunch of fun examples here so that we'll feel confident. Any questions so far? Okay, well, let's do another one here. If you're happy, I'm going to erase that. We're going to do another one. Now, this is what you do if you have an ideal gas. Now, if you have something like water or one of the refrigerants, then we need the vapor dome. Let's do one with the vapor dome. And you're going to read chapter 3 when you get around to it. But the test is on 1 and 2. And there's no official homework that I'm giving you tonight. However, I think you have some homework that's due Sunday night. Yeah, you do. You have some homework due. You might have done it. I think a lot of you have done it already. It's homework number 7. It's 2-110E. I believe it's due Sunday night. Is that right? Let me look and see here just a minute. It's due the 11th. I think the 11th is Sunday, isn't it? No. No, your homework is due tomorrow night. Today's the 10th. Your homework assignment number 7 is due Friday at midnight. It's is it 110E? Is that what it is? Let me check again. I don't want to foul anybody up here. 2, yeah, that's what it is. A lot of you have done it already. I'm kind of behind on my grading, but I'm going to catch up. You'll see. Okay, here's the next problem. Here we go. This is going to be water now. We're going to do water. And let's do water at 300 degrees Celsius. This will be T1. And P1 will be 1500. No, let's make it 15,000 kilopascals. That's state 1. And then we're going to go, we're going to have another isotherm. We're going to have an isothermal process. And we're going to go to P2 is, let's go to 5,000 kilopascals. And, well, if it's an isotherm, the temperature would still be 300, wouldn't it? Okay, great. So what are we going to do? Yeah, well, we could draw it on a PV diagram. That would be fun. And we could find, I'll tell you what, let's do. Let's sketch it on the PV diagram. Sketch the process. I want the process. Remember, a process, it's going to have a 1, and it's going to have a 2. It's going to have a process and an arrowhead on it. Sketch the process on your PV diagram. And while you're at it, why don't you find little v1 and little v2. I'm going to shut up for 2 minutes and let you at least get started on that. And then I'll help you, okay? Now when you do this, can you use the ideal gas law on this? What do you think? Let me ask one of my students here. Let's ask Bryce. Bryce, unmute and tell the class, is it okay to use the ideal gas law, Bryce?
No, it's not okay.
No, it's not okay. You can't use the ideal gas law on this. So Bryce, what do you use?
I'll be using tables.
That's it. Everybody, Bryce knows you got to use tables. I'm going to shut up now. You have 2 minutes. See if you can sketch the process. We're going to find those specific volumes. I'll be quiet now. Well, I don't know if I gave enough time. But if you just woke up from a daydream, what we're doing is we've got water and it's at a temperature of 300 degrees Celsius and a pressure of 15,000 kilopascals. You could write that as 15 megapascals if you wanted to. And it's going to follow an isotherm all the way to a pressure at state 2 of 5,000 kilopascals. But the temperature should be 300 Celsius because it shouldn't change any if it's an isotherm. And we're going to sketch that on a PV diagram. But it's water. So here, let's draw the diagram now. Here's your PV diagram. I think there's enough room. I could even make it bigger, couldn't I? A little bit. Ah, but it's water and it's got one of these things. It's got that vapor dome thing. And to locate where you are, I always go to the saturated table first. Now I call it the vapor dome table. And we're going to look up water. Vapor dome table for water. All right. Okay, I found it. It's on table B.1.1. B.1.1. And we want 300 degrees Celsius. Well, 300 degrees Celsius, I really need the second page on this table. This table goes several pages. But you know what? 300 is kind of up towards the top. It's kind of up here. And this is your 300 degree Celsius. Now, when you get right here, there's a kink. It doesn't come out here and kind of turn. No, it doesn't do that. There's a kink. Here, let me make the kink a little more obvious. There we go. There's a kink right here, and it does that. This actually goes down more. Right, maybe like that. Whereas this isotherm, there's a change in direction right there. And this is the 300 degrees Celsius isotherm. Everywhere on that is 300 degrees Celsius. So see, we're labeling our isotherm and put it in red. Get yourself some red pen or pencil. And there's our PV diagram. And we're going to look up 15,000 kilopascals. Well, this right here at 300 is 8581. This is 8581 kilopascals. Can you find that 8581 on table B.1.1? Can you find it? I'm going to wait till I hear a couple of students say, uh-huh.
Yes.
Yes. I need another student.
Yes.
Yeah. But see, we don't have 8,000 kilopascals. We have 15,000 kilopascals. We're in here someplace. We're at 15,000. Here's our state one. See, at the very tippy top, it's 22,000. If you'll look at the table there, it goes up to 22,000. But 15,000 is in this compressed liquid region. They call it compressed liquid. Well, we have a compressed liquid table. Let's look and help me find the compressed liquid table. Shop around.
B.4.
Thank you so much. It's table B.1.4. B.1.4. And I want you to look up 15,000. Hey, I found it. 15,000, we want 300 Celsius. There it is. Hey, I can get little v1. Let me write it down for you. Well, it would be here. Little v1 is 0.001377. on table B.1.4. It's compressed liquid table. Because see, this is the compressed liquid region. Can you find that 15,000 kilopascals, 300 Celsius in the compressed liquid region? Can you find 0.001377? I need an uh-huh.
Uh-huh.
Just a minute. Let me see who's trying to sell me something now. I don't know who that was. Somebody wanting money, probably, as if I have a lot of money to let them have. Okay, now where were we? Oh yeah. Now I need to find state 2. See, state 2 is 5,000 kilopascals. Let me find that. Oh, hey, look at here, guys. 5,000 is smaller than 8,000. Okay, I'm going to shut this thing off. How do you do that? You push the button and we'll hold it for a while. Yeah, power off. That's what I'm going to do. Power off. Now they can't call me. Good. Okay, now let's see. Where were we? Oh, yeah. Look here. 5,000 is smaller than 8,000. See that 5,000? We know state 2 is 5,300. We know we're on this red line, but see 5,000 is right here. Here's state 2. There's state 1, there's state 2. Now state 2 is in the superheated vapor region. So let's go to the superheated vapor region and let's see if we can find 5,000. Hey, I found it. No, wrong page. 5,000. Here, I found it. 5,000 superheated vapor, 300 Celsius. I'll tell you what V2 is. This is table B.1.3 now. We switched tables on you. We're table B.1.3. B.1.3. And V2 is 0.04532. There you go. Okay, now let's draw the process. Now, do you take a shortcut? You just start here at 1 and just come on down here and draw a straight line to 2 like that? Is that how you do the process?
No.
No shortcuts allowed. No shortcuts allowed. If it's an isotherm, you follow the isotherm. So here we go. Here's our process. We're going to follow the road. It's sort of like the Broken Arrow Expressway. You follow the road. You don't cut through people's backyards. You stay on the road. And here, there's a kink right here. And you follow the road. And then you put an arrowhead right there. Look, there's a 1. There's a 2. There's your process. It happens to be an isotherm in this case. And you put an arrowhead there. That's what I want. I want to see the process. Okay. And look, we got V1 and V2. And we label them. I didn't label V2, but I can put it down here. See it? It's right there. There's the amount. We got temperatures. We got pressures. So we got the pressures over here. Any comments or questions on how to do that?
Professor, this is Nathan.
Yes. Thank you, Nathan.
you have, okay, so on the left side of the vapor dome, we use the compressibility table. And on the right side, we use the superheated vapor table.
Now, Nathan, they don't call it compressibility table. They call it compressed liquid table. It's the C.L. It's the compressed liquid table, Nathan.
Okay.
Did you find the compressed liquid table?
Yes, I followed this problem and I found all the things that you discussed. I just wanted to make sure I understood that concept of the left
Yeah.
side of the vapor dome versus the right side.
Right. This is compressed liquid. This is superheated vapor. Now in here, they call this saturated mixture. Up here at the very tippy top, they call that the critical point. It's a critical point.
Thank you.
Thank you, anytime. Okay, well, great. Let's do something else. Is there anybody else, any comment or question there?
I have a quick question on as far as your isothermal drawing, how do you know exactly what that line is going to look like? Because I'd imagine it's going to look different, obviously, for different like temperatures.
Oh, yeah, like if you wanted a higher temperature, suppose you wanted 350, okay? Well, it's going to be a little higher up. It's going to be more like this. Now, when it's inside the vapor dome, it's flat. I just drew the 350. It's hotter, see? But now they have them lower. If say you're down here, this would be the 250, okay? The 250 degree Celsius isotherm. Now here it's going to be flat. It's going to be flat. And then there's your two. I don't know if that answered your question.
Yeah, so pretty much no matter what, as far as shape, it's going to take the same shape every single time. Like as far as like
it has this.
top
It
being
has
flat.
this. It has the same shape.
Okay, that's just what I need to know.
Now, one day, I forget when it was, I explained how they got these vapor domes. Let me briefly just go back over that to tell you what they did. They did some experiments, some isothermal experiments. And on the experiments, they had a whole bunch of isotherms that they were able to draw. You could have a dozen of them, okay? And then somebody, some intelligent person said, hey, let's connect the dots. You see these places here where there's a very definite change. Some bright person said, I'll tell you what let's do. Let's connect the dots. So they did this. They connected the dots. Now it turns out it comes up here and it does this. And that's how they got the vapor dome. Now this very tippy top, that's where you have your critical isotherm. See, the critical isotherm, it comes down here. It has an inflection point, and it does that. And anything up in here is called a fluid. It doesn't have a vapor, a mixture, and a liquid. It doesn't turn to liquid. They call it a fluid, but it does not change the state to a saturated mixture, and then it does not change into a liquid. I showed you that one day, and you could probably look at that YouTube video, but I couldn't tell you what day it was. Okay, let's do a different one, unless there's another comment. All right, let's do another one. Okay, now this one is, let's see which one I want to do now. This one's R134A. Now that's a refrigerant. That's the refrigerant in your car air conditioner. I bet you all have some R134A out. I was going to say out in the parking lot, but in your case, it's in your driveway maybe, or at the apartment house parking lot, wherever you live. But let's say you had some R134A. Okay. And what we're doing now is we're practicing PV diagrams. That's what we're doing. And we're going to do one with R134A. It's a refrigerant used in your car air conditioner. And we're going to start with a saturated liquid. And we're going to go to, we're going to have a process, and we're going to go to a saturated vapor. We're going to go from saturated liquid to saturated vapor. Now, being lazy, instead of writing that out, we'll just go S dot L dot, saturated liquid. And we're going to go to S dot V dot, saturated vapor. Now, the process between those is going to be a isotherm. Just a minute now, I'm getting mixed up. We're gonna do it at 0 degrees Celsius isotherm. All right. Now, here's what I want you to do. I want you to sketch the process on a PV diagram. I want you to sketch it. And then I want you to find, let's find the pressure at 1 and the pressure at 2 and specific volumes at 1 and 2. Why don't I shut up for a minute and a half and do that. Now to do that, you really need to find that table in the back, someplace in the back. There's R134A. Yeah, I found it. You can find it too, and I'll be quiet. Let's see if you can sketch the process. Go for it. Well, I don't know if that was enough time for you guys, but maybe. Let's do it, shall we? We're going to draw the vapor dome now. See, this has a vapor dome. It's not an ideal gas. You'll have to go to a table. Looks like B.5, B.5.1. That's the name of the table. B.5.1. Yeah. Okay, well, let me make a little room here and we'll do that. Do I have enough room here? Yeah, I think so. And here's your vapor dome. Here's your pressure. Here's your specific volume. And on this table, it's helpful to me to see what the pressure is up here at the top. According to this, the pressure at the top is something 4,000 and something. 4,000. We don't know our pressure, right? Let me find the zero. Oh, I see it. There's the 0 Celsius. You know what? It's kind of in the middle, isn't it? It's kind of in the middle. This up here is 4,000 something kilopascals, and this is only 294. They're not linear though. They're logarithmic. Here, let me write that. See, this pressure here is 4,064 kilopascals, but the 0 Celsius is right there in the middle. The 0 Celsius, and here I'm going to draw the isotherm now. And there's a kink right there, and it goes down like that. There's your 0 Celsius line. There's another kink right there. That's 0 Celsius. That's your 0 Celsius line. And the pressure there is 294. And you wonder, 294, that looks halfway. Halfway should be about 1,000. But see, these are not linear. They're logarithmic. I don't know if you've ever looked at a logarithmic scale. They have these big gaps here, and they get smaller and smaller and smaller and smaller and smaller and smaller. It's logarithmic. In fact, these PV diagrams are really logarithmic. Okay, well, here's our state 1 right here, and here's our state 2 right here. Oops, state 2. State 2 is right there. And you know what? The pressure at 1 is equal to the pressure at 2. It's 294 kilopascals. Now, our process is right here. It goes from 1 to 2. Put your arrowhead on there. Here's our process. Now, that process is isothermal and isobaric. It's constant pressure inside here, and it's constant temperature inside here. They have a name for that. It's called boiling. So you got all liquid here, you got all vapor, you got, in case of water, it'd be steam, but this isn't water, this is R134A, but it's all vapor here and all liquid there. They have a name for that. You can call it boiling or you can call it evaporation. See, guess what? This takes place in the evaporator. You've got an evaporator in your car, and see, that's what cools you off. See, when a liquid evaporates, that cools you off. Go jump in the pool, get out where it's windy, and let the wind evaporate that water on your skin, and you cool off. Can you relate? If you're all wet and you're standing in front of a fan, that cools you off, doesn't it? See, evaporation cools you off. That's how air conditioners work. The evaporator cools off the air that's blowing over the evaporator, and it makes your house cool or makes your car cool. So there's your process. It's an isobar. It's an isobaric process. It's also an isotherm. Boiling's the same way. Take a pan of water, put it on the stove, and boil it. Well, the temperature, once it starts boiling, water boils at what, 212 Fahrenheit or 100 Celsius at standard pressure, and it stays that temperature. If you put a thermometer in there and it says 212 when it starts to boil, let it boil for 10 minutes. Now the water level will go down in your pan if you're boiling water because it's converting to steam, but the temperature still is 212 because it's isothermal. And the pressure is constant because you got the pressure, air pressure in your kitchen. It doesn't change just because you decided to boil some water. The atmospheric pressure stays the same throughout the boiling of water in your kitchen. Okay, now if you wanted the specific volumes, we'll just read them off the table. It says here, it's state 1. See, what you look for is this little VF. At 0 degrees Celsius, it's 0.000773 cubic meters per kilogram. State 2, that's little V sub G. There, at 0 degrees, it's 0.06919. There we go. We found the pressures, we found the specific volumes, we found the temperatures, and we drew our process. Any question on our example here with your R134A?
Mr. Griffin,
Yes.
just a quick question. So I'm a little confused why, I know it is an isotherm and isobar, but I know in the
Yes.
isotherm the temperature remains constant, but why the pressure on this isotherm is also constant?
I didn't quite understand that last thing, Mohammed. Why is the pressure on this side
Yes,
constant?
yeah, because it's an isotherm. In an isothermal process, the temperature remains constant, right?
Right.
So why the pressure is constant in this one? I mean,
Well,
why the
see,
pressure is same, P1 is equal to P2.
on this graph, Mohammed, the pressures are over here, and you're going from here to here, and the pressure stays the same inside here. Now, the pressure doesn't stay the same here. This will have a higher pressure. And here, down here, that'll have a lower pressure. But see, we're going from saturated liquid to saturated vapor. We're just going from here to here. Pressure doesn't change, temperature doesn't change from here to here.
Oh,
I don't
okay.
know.
Okay. Okay. Got
You're
it.
okay?
Yeah, I got
He's
it.
okay. All right, good.
Thank you.
You are very welcome. Well, let's do one more. All right, this one is, we'll go back to water now. Any other comments or questions before we do water? Okay. Let's do an isobar with water. We've got water, H2O. And we're going to have 100, we're going to have an isobar. We've been doing isotherms, Now, one of them turned out to be an isobar also, but we've been doing isotherms. But this one's going to be an isobar, and it's going to be at 100 kilopascals.
Mr. Griffin,
Yes.
can we do one with the isocruit instead of isobar?
You want to do an isocore?
Yeah, instead of isobar. If you can just show an example of that.
Yeah, I would love to.
Thank you.
Yeah, Mohammed wants to do an isocore. Okay. Well, let's do an isocore. I was going to do an isobar. We got time, Mohammed. We got 18 minutes. We'll do both. Now we're going to take an isobar and we're going to go from state 1, which has a quality of 50%. Now the pressure at state 1, if it's an isobar, of course, is 100 kilopascals. But it's inside the vapor dome and it has a quality of 50%. And then at state 2, well, at state 2, if it's an isobar, we still have 100 kilopascals, but the temperature is going to be 150 at state 2. 150 degrees Celsius. See, the temperature here, we don't know. You're going to find out. And we're going to draw the process on a PV diagram with an isobaric process. And then in a little while, we'll do an isochoric process. Okay, now what are we going to do? Well, we're going to sketch the process. Sketch and label. Is that how you spell sketch? I think so. Sketch and label this isobar. And then find, well, you can find T1, V1, and V2. We know T2 and we know P2, but we don't know T1 and we don't know V1 or V2. So I'm going to again shut up and let you work on that, and then we'll do an isocore for Mohammed. But go ahead, I'll give you a couple of minutes. See if you can sketch that. Well, in the interest of time, I'm going to go ahead and draw this PV diagram. Now we know the pressure is 100, and it stays the same because it's an isobar. So let me draw my my vapor dome. Now 100 is down here pretty low. 100, does that show up? Yeah, 100 kilopascals shows up there. But see, if you have a quality of 50, that puts you down in here someplace. Here's state 1. and you can look up the temperature. What does it say for 150 degrees for water? I'm on the wrong table here. Okay, now I need 150 degrees. No. I'm sorry. I need 100 kilopascals. 100 kilopascals. Okay, I'm going to draw my isotherm now. For if you have 100 kilopascals, here it is. This isotherm is 99.62 degrees Celsius. And we are located right here at state 1. See, this is 99.62 degrees Celsius. I'm on table B.1.2. And we're right here. Now you could, we just found T1. Do you have any questions about the T1? You just look it up. It's in this table. Now, if you want V1, here's how you get V1. You go VF plus your 50% times VFG. Okay, well, we can do that. We know what VF is at 100 kilopascals. It is 0.01043 plus 0.5 times, I'm running out of room here, 1.69296. So we can get that in a minute. We can get V1. It's just a matter of plugging that in. Now we're going to go to 150 degrees Celsius. Well, see, 150 degrees Celsius is out here someplace. 150 is hotter than 99. They kind of got squished together there. But 150 degrees Celsius is out here. And if you follow an isobar all the way to 150, here we go. Here's 1. And there's your arrowhead. There's state 2. This is what your process looks like. You're out there in the superheated vapor. And so where do you look up your specific volume at 2? Well, you just go to 100 kilopascals in your superheated vapor table. Let me find it here. Now, there it is. And you look up 150 Celsius and you just read it off. Here we go. V2 is equal to 1.93636. So we got the V2. You just read it off the table. Now that's table B.1.3. B.1.3. So you can get V1 here. You can get V2 there. We sketched it. What else were we supposed to do? Find P2. Well, P2 is the same if it's an isobar. They give you T2. We found T1. Yeah. Hey, we're done with that. Let's do an isochore for Muhammad, and then we're going to run out of time. Okay. Let's go ahead and get this and we're doing isochore, and we'll go up here. We're going to go straight up, Mohammed. But instead of going in isobaric to 2, we're going to go, see, this was state 1 right here. We're going to go to our state 2 right here. Maybe you should call it state 3. We don't want to get confused because we already have a state 2 way out here. We're going to go up straight up. Let me get this specific volume here. Let me plug that in. And it will be if I plug that in correctly, V1, of course, that's going to equal V2 if it's an what's the word? Isochore. They call this an isochore. It is 0.8475, blah, blah, blah. So we have this. We have 0.84752 cubic meters per kilogram. It's the same at 1 and it's the same at 3 because it's an isochore. Now, here's the sort of thing they could ask you. They could ask you what the pressure is there at 3. Well, I don't know. Go to your table, your saturated vapor dome table, and look up 150 Celsius and tell me what the pressure is. It is 475.9. This pressure right here is 475.9 kilopascals. So if you started at state 1 and you had an isochore to state 3, that's your new pressure. And you're on 150 Celsius. And if you wanted the specific volume, well, it's the same. V1 and V2 are the same. But what about the quality at state 2? I need a little room here. Here's how you would get the quality at state 2. V2 would equal the VF plus the quality at 2 times VFG. Now V2 is the same as V1. It hasn't changed any if it's an isochore. What was V1? That was the 0.84752. Mohammed, you can look those up in your table, and you can find the quality at state 2. Let's look them up. Go to 150, and we're going to write these down here. They are 0.00109 plus the quality of state 2 times just a minute now. I'm having a little problem here now. Did we get that right? The 0.84752? I'm getting confused, guys. I just had a senior moment, and now I'm totally confused. I'm not confused about our graph. I'm just confused about the V2.
I think for V1,
Yeah.
I might be showing, I think I'm showing 0.815843.
Oh,
You can do
really?
it one more time. Yes.
Really? Oh, gee, and we only have 2 minutes left. Mohammed, I'm so sorry. Kind of ran out of time on this. Did we get, let me get this V1 right at least. Now, V1 at and we're doing 100 kilopascals. Okay, let me check that. 0.001043. 0.0010, that's right. Plus the quality is 0.5 times 1.69. Yeah, we did that. And when you do that, do you get that? I think so.
Yes, yeah, you do get that.
Okay, so we know that. So the quality, the specific volume at 3 should be the same. Here, let me write that. The specific volume at 3 should equal the specific volume at 1, because you went straight up. And several of us got 0.84752. 0.84752. But see, that's at 150. You see, it goes up to 150. So let me find the 150, and the 150, I found it. Here it is. Yeah. Now here's the problem. The 0.8 is bigger than this VG. So here's what your vapor dome is doing. Your vapor dome doesn't do that. It does this. It comes up here and it goes like that. And your state 2, I'm sorry to confuse everybody, but your state 3 is outside the vapor dome, because the at 150, this VG is smaller than your 0.84752. And so you went outside your vapor dome. And what you could do, there isn't going to be any quality. I'm sorry. There is no quality at state 3. You're going to have to go to your superheated vapor table if you want to find your specific, well, you know your specific volume, but you could find your temperature. It's not going to be 150, because see, 150, oh gee. Hey, I'm out of time, guys. This 150 comes over here and it dips down below that. It's actually hotter. Wish I had more time, Mohammed, to do that carefully. But we're out of time. It's sad. Here's your last chance to say something quick. Go ahead. Okay, you're out of time. I'm going to sign off, and I will see you Tuesday. How's that? Yeah. Work
Thank
on.
you.
Bye-bye, everybody. And what about your exam? Is that, when's your exam? I forgot.
Professor, our exam is this week or today to Sunday.
Yeah. I think you can do your exam and turn it in. Yeah. Now your homework's due tomorrow, but I don't think the exam's due till Sunday night at midnight. Isn't that right?
Yes, sir.
Yeah, I think we're okay. Okay, guys, enjoy. We'll see
Thank
you
you, sir.
then.
Bye.
Bye-bye.